Okay, so back to the area of a square function. F of x is x squared. And so we can think of this f of x function as an amount function. An amount where, what? Give it a side length. This function cranks out the area of the square. The amount of the area of the square, right? So we want to find f's rate of change function. We want to find f's rate of change function. What are we going to do? Can you do the first step? I want to find the rate of change function for this particular function. F of x equals x squared. What would the first step be? Forgot my list, but I can call on you by shirt color. Okay? Bring my list on Thursday. So, what will the first step be in finding the rate of change function for f of x equals x squared? Right here in the gold shirt. You know what the first step would be? What's that? That's not the first step. So yes. So you know the rule that we're getting to later. We don't know that yet. So what is the yes, sir?
You set up like f of x plus h minus f of x.
Yeah. So. This is where we live right now. Technology. There it is. All right. Here we go. So he said, do we do f of x plus h minus f of x all over h? Yes, this is the land we're living in right now. This is our rate of change function. Given any function f as an amount function or an accumulation function, this is the rate of change of that function. It's the rule for a new function. We call this r sub f of x. And is this exact or approximate rate of change? Could be either, right? Could be either. It just depends on how big h is, right? If h is not small, then that will be approximate. We'll get an approximate result based on whatever h is. And then, but if h is small enough, then it's exact. So exact would be, if we put the limit, and this is just notation for the same thing we've been talking about. H is really small enough so we can't tell the difference between exact and approximate. But without the limit, it's like either, right? It's like either, but with the limit as h approaches 0, it's exact. Okay, so for RF, so then this thing equals, what would that equal? Right here in the green shirt. So if f of x is x squared, then what does that difference quotient equal? Okay, so you're looking at this part right here. Yeah, this function just says take the input and square it. What's the input for this first one? X plus h. So the rule says take that thing and square it. It's one of the easiest rules that exists, right? Just take whatever you're putting in and square it. We're putting in x plus h. Keep going. Right? That's f of x over h. Okay, so this is the rate of change function, an expression for the rate of change function for this particular function, f of x equals x squared. Okay, and then we're off to the races with algebra here. So what is x plus h quantity squared? X squared plus? We all know that there's a middle term, right? And then h squared. what happens in the numerator? X squareds go away, right? Got a plus x squared and a minus x squared, so I got 2xh. H squared all over h. And I want h to be really, really small. And so the problem is that h in the denominator. So my goal is always to get rid of that h in the denominator. That's kind of where we're going with this algebra. How do we do that? Yeah, now after we subtracted those x squareds, everything has an h in it. So we can factor out h. We get 2x plus h. And so we end up with 2x plus h. What does 2x plus h mean? What is that? It's going to give us? That's the rate of change function, right? That's the rate of change function for picking an interval of h, right? Picking an interval of h. So now if we want exact, we want the exact rate of change function, then this thing becomes just 2x when h is essentially 0, right? Here's another way. So that's an alternate notation to the limit thing. So I can say that thing will eventually be 2x when h is 0. So look, so we got a what? So is this, first of all, is this the rate of change function or accumulation? Rate of change, exact or approximate? Exact. Is it represented in open form or closed form? Closed form, right? So we got a closed form, exact rate of change function for the area of a square. Okay, so when the side length is 9, 18 is what? It's the rate of change of the area with respect to side length. And that 18 is a value of rate of change. So all that we learned about rate of change it applies, right? It's 18 what? Inches squared per inch. Inches squared of area per inch of side length. So how do we interpret that? Given any what? Change in? Given any change in side length.
The corresponding change in area is 18 times the change in side length for the moment around 9 inches.
Did you hear that? That was worth the recording. That was awesome. All right, he said, given any change in side length. And at the end, he said, for any moment, or at the moment, 9, when the side length is 9, okay, for a small change in side length, the change in area will be 18 times whatever that change in side length is. Okay, but if we get outside of the moment around 9, then we're going to have a different rate of change, right? So when we get to 10, when the side length is 10, now the rate of change is 20. So we can't say that anymore, right? We can't say that anymore. Okay, very good. Okay, so now let's talk about this. So we're in this journey of accumulation to rate, but now we've opened the door to now write these accumulation functions in closed forms. Let's finally do that here. Let's finally do that, and you saw it in your homework. Okay, what we just learned that if f of x equals x squared, the rate of change of f is 2x. So how else could f be expressed? How else could f be expressed if it's rated, given that its rate of change is 2x? Reaching back into the past here. So forget that you know that it's x squared. Now you know the rate of change of f is 2x. How could you express f? What's a new way you can express f? Volunteer. Yeah.
Integral beta x 2x dx.
Okay. Almost. So you just have this one the one technicality there. But yes, you got the idea.
Oh, sorry. Beta t 2x dx.
Okay. Yeah, we'll do the other way around, right? So we'll do in this case, since area of a square starts at 0, we could say it's from 0 to x, 2t dt. Right, so if we have the rate of change function, we can represent it, the accumulation, or the net accumulation from 0. In this case, it's the same as total accumulation, because its area of the square is 0 at 0, as 0 to x 2t dt. Okay? But we know what f of x is, right? So now we know what that open form integral is in closed form. What's that open form integral in closed form? If it's f of x. All right, so let's just go generically a. So we know that thing could be written in closed form as x squared for some value of a, because it's equal to f of x, which was x squared. So as before, when we saw that integral, a to x 2t dt, we just had to stop. But now we know where that rate function came from. It came from the amount function x squared. So that's our closed form for that open form accumulation function. Does that make sense? Okay, so now you're going to try. So last week we learned that the rate of change function for volume 4/3 pi x cubed, we showed it in closed form was 4 pi x squared. Okay, so then we learned something else. Can you write down what else did we learn besides the fact that 4 pi x squared is the rate of change function for volume of the sphere? What else did we learn? Could you write it out? Give it a shot. Anyone think they got something here for this? Something new. You had a great answer before, so you got it? Yeah. Integral of? Can I do t? dt from what to what? Let's do a. So just start at any a. So what we learned is this open form expression that we might have seen before, now we could write it in closed form. What would it be? For some a. So before, when we had an open form expression like that, we had to stop there and if we wanted to calculate some accumulated volumes of a sphere, we'd have to get GC or some technology to do it for us. But now we know that it has to be 4/3 pi x cubed. Because that's the volume of a sphere, right? That's the volume of a sphere. And so we know now we have a closed form for that open form accumulation function. Does it make sense? Yeah.
How come on the previous equation, the red, it's limited from greater than 0 to x, and then when you go down to blue, it's a to x?
Yeah, so we did a down here. So I just make it more general.
Okay.
All right.
So it doesn't have to be limited.
Yeah, so I'm just making it more general to starting at any value a.
Okay.
But I kind of started out there with 0 because squares, the area is 0 when side length is 0.
Okay.
But then I moved to more talking about it more generally. Okay, I guess that wasn't. All right, so doesn't make sense. Any questions? Okay, so let's talk about some big picture stuff and how things are fitting together here. So things that we're learning, how are they fitting together? So we've seen that if you have a amount function f of x, we could find its rate of change function. And then what we just did is we found what? We found we could write a net accumulation function given the rate function. We did that before. And then the last step would be, could we write the original function f in terms of the net accumulation function? And we've done that before too, for exam 2. So let's work through this whole process. So f of x is, we're starting with an amount function that gives some amount for any value of x. How do we find the rate of change function for f? How do we do that? How about right here in the red shirt? How do we find the rate of change function for f? What's that? Yeah, where does that come from? Okay, how about the next one? Right, good. So that's the exact rate of change function is the f of x plus h minus f of x over h, right? For small h. That's the exact rate of change function. Okay, and then we can build back what? A net accumulation function, which would be like what? What would the net accumulation function from that rate function? What would that be? How about in the ASU hat, the gray hat there in the background? Yeah. Uh-huh. Right. The integral from a to x of that rate function, dt, rf d dt. So what would that? That'd be exact net accumulation, right? Starting at any value a, we're going to start accumulating at that rate function that we just found, the f of x plus h minus f of x h. So then, who remembers, how do we get now the amount function, what total accumulation function, or the amount function given the net accumulation function? Who remembers? How do we do that? Yes, sir. Right, the starting, so everything that's accumulated up to a, we're going to add that on, and how do we express that? What is everything that we have up to a? What's the total amount we have up to a? No. Remember what we added on to the net accumulation function to get the, f of a, right? F of a. So the amount function can be written as f of a plus the net accumulation starting at a. Remember this? So we've come full circle, right? We come full circle. We build the rate function, we build the net accumulation. If we add how much we have before the net accumulation, then we're back to the total amount again, total accumulation. So that f of x that we started with could be written this way: f of a plus the net accumulation starting at a, changing at that rate. Okay, so here we go. So this is the conclusion from that previous page, and then we could take it one step further. We could, what would it mean to subtract f of a from both sides? If I subtracted f of a from both sides, I would get, right, f of x minus f of a would equal the net accumulation. So what is this? So what does this mean? It means the net accumulation starting at a is what? Is the total change in amount starting from a. It's like two different ways of saying the same thing. So the net accumulation from A to X at that particular rate. So this is open or closed form? Open form. It's representing what? Adding up all the little bits of accumulation, right? Like our long accumulation function. Summing up the bits of change. Each one calculated by rate times change in X. Rate times change in X plus rate times change in X. And we're going to sum all those up and get the net accumulation starting from A to X. And when we do that, we get, when we sum up all the little changes, we get what? Total net change from A to X. Final minus initial, right? Final value of the quantity minus initial value of the quantity. Total net change from A to X. Super important. This is kind of the pinnacle of the course. It's like everything we've been working on comes to this point. That the net accumulation from A to X can be expressed as the total change in the amount from A to X. Should make perfect sense. And so then this is also the key to writing closed form, right? So if we had a closed form representation of F, then we'd have a closed form representation of that net accumulation function. If we know what the function F is, then we can write the net accumulation function in closed form as f of x minus f of a. So for instance, we want to, if I express this right here, I'll do it in blue. So the example, so if I express the integral from 4 to x of 4 pi t squared dt, what does it mean, and can you write it in closed form? What does it mean, and can you write that expression in a closed form? It's not on your smartphone. Go. So tell the person, first of all, what's the meaning of that expression, and then can you write that expression in closed form? Go. I should have done 4. Okay. Somebody new. What's the meaning of that? Somebody new. Volunteer. Other than the white hat back here in the tank top. What's the meaning of that expression, first of all? Okay. And so do you know what is the net accumulation for? Net accumulation of what? Thinking back to a recent example. How about right here in the maroon shirt? Yeah. Net accumulation of what quantity? Not sure. Yeah. No, I'm not looking for an expression. I'm looking for what quantity is the net What's that? Okay, that's the rate of change. That's right. So 4 pi t squared is the rate of change. Rate of change of what quantity? Volume of sphere, right? So it's the same example, volume of sphere. So this whole thing is what? The net accumulation of volume starting from what? What's 4? Radius is 4. So as the radius starts at 4, and then the volume grows at a rate of 4 pi t squared, this will be the net accumulation of volume starting from a radius of 4. Okay? And so, according to this, what we said, that's equal to the total change of some function. What function? What is the function f? That was the total volume function, right? What's the function f? 4/3 x cubed, but is that it? Minus 4/3 4 cubed. This is the closed form expression for that open form integral. Both of them give how much the volume grows, starting at 4 up, when the radius starts at 4 up to x, but they express it in different ways. That expresses it as the sum of lots of little changes, right? The sum of lots of little changes. This just gives you that total amount of change, right? It's the total amount of change in the sphere's volume starting at 4 up to whatever x is. And so you plug in 8, it'll tell you the change in volume of the sphere as the radius changed from 4 to 8. Plug in 20, it gives you the change in the volume of the sphere as the radius changes from 4 to 20. Does it make sense? So this is what? Net accumulation of volume of the sphere starting from a radius of 4, which is equal to the total change in the volume of the sphere starting from a radius of 4. Questions? Super important. Okay? All right, so this essentially is, we'll keep talking about it as we go, but this is the fundamental theorem of calculus. It's kind of the pinnacle of the whole course. We're drawing on so many things that we've learned so far this semester to come to this point. It deserves not 1, but 2 exclamation points. Okay? This is the fundamental theorem of calculus. Okay. Not that. Let's see. So let's talk about, we'll do that on Thursday. We did those already. Okay, next one. 11. Okay, so we want to start, because we can get these rate of change functions in closed form, we're going to start developing some rules for those, some basic rules for what the closed form rate of change function will be in very specific situations. Okay, and so then that's what the mastery test is about. So the mastery test is about a very, very specific window of content in the course. It's about that you know these rules that we're about to start learning. It's very much memorization and algebra. It's going to feel like much different than everything we've done so far. So you need to learn these rules and know how to apply them. And it's memorization and algebra. Memorization and algebra. So the first type of function we want to talk about is a constant function. So just to clarify, the mastery test is not mastery of the course content. It's mastery of a very narrow window of the content, which we're starting now. Okay? We're starting now. Okay. So constant functions. So if an accumulation function never accumulates any changes in its value, right? It stays constant. What is the rate of change? 0, right? 0. So the rate of change is 0 for any change in x. Y doesn't change. For any change in x, y doesn't change. So the rate of change is 0. Okay? How would we show that mathematically? What would we do? How would we start? How about in the blue tank top and the white hat? How would we start? Yeah. So what would we start with? That's right. Not sure. How about in the light blue shirt right here, or grayish shirt on the end? Nope, in front. In the t-shirt, yeah. Here. How would we start? We want to find a rate of change function for a particular constant function. What would we start with? I'm not sure. How about next word? What's the formula? Right. If we want to derive any rate of change function, it's always going to start with that. It's always going to start with our f of x plus h minus f of x over h. Okay? So f is a constant, c, and so we're going to start with this every time. If you want to figure out what a rate of change is, it will always be this. But then what we're going to do is we're going to use this to come up with some rules so that we don't have to use this anymore. Okay? That's the point. So what is, if f of x equals c, what does that say? It says no matter what you plug in for x, the value is, so what's f of x plus h? C plus h? What does the function say? No matter what you plug in for your input, you get an output of c. So it's just c, right? So f of x plus h is c, f of 8 is c, f of negative 18 is c. Everything is c. Doesn't matter what you plug in. So we get c minus c over h, which is easy, right? 0. Doesn't matter how big of h you pick. For this particular one, doesn't matter how big the h you pick is. You still get 0, okay? So there's no approximate exact. It's always exact. If you have a constant function, rate of change is 0. Rule number 1. So we just learned one rule. Next one is constant multiple. Okay, so what does that mean? Constant multiple. So here's an example. At every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? If he's always gone 5 times as far as her, then what's his speed relative to her speed? 5 times as fast, right? 5 times as fast. So that kind of embodies the idea of the constant multiple rule. So what? F is equal to 5 times g, right? That's what the given said. And so then what's the conclusion then? The conclusion would be that in this red statement, well, how could you write that red statement with function notation? What conclusion do we make? How could we represent it mathematically? Volunteer. Yeah.
Any moment f of g is 5 times greater than, or excuse me, f of x is 5 times greater than g of x.
Okay. But so how could we represent the reds? So that's what we've written there. Now I want to write that at every moment in time, John's speed is 5 times Mary's speed. How do we do that? Because that's distance, right? The distance equals 5 times Mary's distance. What about speed? How about right behind him? What is speed relative to distance? When you're talking about distance, then what is speed relative to distance? Yes, ma'am. 5x. What is speed relative to distance? It's the rate of change, right? Isn't speed the rate of change of distance? So what would our next equation be that represents that red statement? Every moment in time, John's speed is 5 times Mary's speed. So, someone saying that? Where's, is that, okay, go. Yeah. 5 r of f of x? Yeah, so John's speed is, John's speed is 5 times Mary's speed. So notice something here. This is an important distinction. When you just have a constant sitting by itself as your function, What's the rate of change? We just learned it. 0. But when you have a constant times a function, does that rate of change become 0? So you notice they're both about a constant. We're taking a constant times one function. We want the rate of change of that. Does that become 0? No. You hold on to that constant, and it's 5 times the rate of change of whatever function you had to start with. So it's only when constants are sitting by themselves that if the rate of change of that would be 0. If the constant's multiplied by another function, then the rate of change is just that same constant times the rate of change. Okay, in terms of the derivation of that, I think that'll be a little homework exercise. So we'll just leave that to you. But that's the rule. The rule is if you have a constant times a function, the rate of change is that same constant times the rate of change, right? 5 times R of G. All right, next one. So we got 2 rules. If you have a constant by itself, the rate of change is 0. If you have a constant times a function, the rate of change of that is constant times the rate of change of that function. Okay, what about the rate of change of the sum of functions? Rate of change of the sum of functions. So I want to know what the rate of change of k is. I want to know what the rate of change of k is. How am I going to start? What am I going to start with if I want to know the rate of change of k of x? Somebody new. How about in the plaid shirt there? Yeah. So if I want to know the rate of change of k of x, that's what I'm interested in. What would be my first step? No, that's the conclusion we're going to make at the end. So I want to know what the rate of change of k is. What do I know for sure? So you're assuming what the rule is, but I want to know what the rate of change of k of x is. That's somebody new. Yes, sir.
F of x plus g of h.
Well, I want to know the rate of change of k. I want to know the rate of change of a function called k. K of x plus h minus k of x over h, right? So we've used f so much that we've just gotten we've kind of become numb, right? But the reason we use f of x plus h is we always called that function f, the function that we wanted the rate of change of. So now if our function is k, then the rate of change of that is k of x plus h minus k of x over h. So we know that for sure. Right? That's our trusted form. This is what we can trust. So now the question is, what is that? What is k of x plus h? What is k of x? And then now we're going to apply the rule for k of x to this ratio, right? To this difference quotient. We're going to apply that rule k of x. It equals f of x plus g of x. So why don't you guys give this a shot? So she actually gave what the final result is. All right. So our goal is that the rate of change of k is equal to the rate of change of f plus the rate of change of g. That's the goal. Okay. But we have to get there, right? We have to prove it. So we have to get there. So start with this, and you have to follow the math through to come to that conclusion. So can you keep going? Give it a shot. So you're going to isolate, right? I'm just kind of giving you a... Okay, go. Okay, so rewriting k of x plus h is really just about knowing what does the rule of k, what are these set, what's the instructions for k? So if you have an input into k, what does that set of instructions tell you to do? It says take the input and do what? Put it into f, also put it into g, and then add them together. Do you see that? That's what k says. That's what the function k says. Take the input, put it into f, take the input, put it into g, and then add those results together. So now we have k of x plus h. What are we going to do? What's the input for k of x plus h? What's the input of k of x plus h? No, what's the input? This is my question. What's the input into k of x plus h? X plus h. So follow the instructions. Take x plus h and do what? Put it into f, put it into g, and add them. That's what the rule for k says. It says put the input into f, put the input into g, add them. And now our input is k x plus h for the blue. The input's x plus h. Follow the instructions. So this is what we got. K of x plus h is f of x plus h plus g of x plus h. Plug the input into the two functions and add. K of x is just what we started with. And so now what are we going to do? Someone who got it. I know someone got it. So where do we go from here? Yes, sir. Right. So you're going to rearrange things. So we're going to move the f of x plus h and the minus f of x together, and the g of x plus h and the minus g of x together. Did you get from there? Split the fraction. Those are then each of those individual things are both over h, right? It's like pulling apart the fraction into two fractions with the same denominator. What's that? Those are your two rate functions, right? So then you should recognize the first one as the rate of change of f, and the second one's the rate of change of g. And we got it. So it's exactly what we hoped for. We hoped that if you're adding two functions and you want the rate of change, that you would just take the individual rates of change and add them together, right? It's like what we would want, right? Make it really easy, and that's what it is. But this proves it. This proves it. Questions on that? Derivation. 3 rules now we got. We got 3 rules already. Once we learn the rule, we don't have to use the f of x, the trusted form anymore. We can just apply the rule, right? So if the function is a constant, what's the rate of change? 0. If the function is a constant times another function, the rate of change is? You hold on to the constant and you take the rate of change of g, and you multiply those. And then if the function is a sum of functions, the rate of change is the sum of the rates. The sum of the rates. Okay, so rate of change of a constant 0. Rate of change of a constant times a function is that constant times the rate of change function. And then the rate of change of a sum is the sum of the rates of change. Okay, so we're going to do one more today, a little more involved. But so what I'll have you do is just don't try to copy everything down because we won't be able to have time to go through it. So you could watch the video later if you want to take notes on it. But the next rule we're going to do is for x to any power, okay? So x to the n. So we need something. First, we need a reminder about binomials. If you have x plus h squared, there's that middle term, 2fx h. If you have x plus h cubed, you get more middle terms. So the higher your power, the more middle terms you get. All right, you'll get actually 3 middle terms with x to the 4th. So then, generally, for x to the n, so notice they all start with x to whatever your power is, so x to the n. And they all finish with h to the, so here it ends with h squared, ends with h cubed, ends with h to the 4th. So this is going to start with x to the n and end with h to the n. And then generally what happens as you go like this is powers of x, what? Decrease each term. The power of x decreases by 1, and the powers of h increase by 1. So that's really all you need to know. So powers of x decrease by 1 each term, and powers of h increase. So this first term has a power of h of 1, and the next one h squared, all the way to h to the n. So we're going to need that. We're going to need that expression right there. And that could work for any n, right? We know there's going to be a bunch of middle terms. But it's going to start with x to the n, end with h to the n. For each term, the powers of x will decrease and powers of h will increase. So we want to do f of x equals x to the n. Everyone write down the first step. We want to know what the rate of change of this is. What's the first step? Everyone write it down. We want to know what the rate of change of x to the n is. What's the first step? Volunteer. Volunteer. Someone you knew? What's the first step? Yes, ma'am. Yeah. She said x plus h to the n minus x to the n all over h. Is that what you got? Good. Yeah, so we're going to start with our trusted form, and then f of x plus h is going to be x plus h to the n. F of x is going to be the x to the n over all over h. Okay, so now here, there's that x plus h to the n. We're going to use that expression we had at the end of the last screen. Okay? Don't let it freak you out. It didn't freak you out on the last screen, so it shouldn't freak you out on this screen. Okay? So now notice what happens. The first term is x to the n. So is that minus x to the n. So those can go by, right? Those can go bye-bye. And now what's true about every remaining term? They all have an h in it, right? Because starting with the second term, it has h to the first, and the h powers go up. So now every remaining term has an h, and we can factor it out. Factor out that h over h goes away, and we get n times x to the n minus 1. And then what's true about all the rest of the terms? Starting with the second term, those all have an h. What we want the exact rate of change, which means h is essentially 0. Essentially 0, which leaves us with nx to the n minus 1. So when the values of h are small, our rate of change of x to the n is nx to the n minus 1. So you think about taking that exponent to follow this rule, move it down in front, take the n and move it down in front, and then reduce the exponent by 1. Nx to the n minus 1. So that's the rule for the power rule. So the power rule is n times x to the n minus 1. Constant function, rate of change is 0. Constant times a function, rate of change is constant times the rate of change. And the rate of change of a sum is the sum of the rates of change. We've got 4 rules under our belt. Quiz Thursday.